Welcome to this comprehensive guide on modular architecture and scene transitions in Unity 3D, designed specifically for beginners. Today, we'll explore how to build organized, efficient, and visually appealing game structures, equipping you with essential knowledge for robust game development. Modular architecture is a design principle that breaks down a system into smaller, independent, and interchangeable components, making complex projects manageable. This approach significantly enhances collaboration among developers, simplifies debugging processes, and makes your game much easier to scale and maintain over time. Scene transitions are the visual and functional changes that occur when moving between different game levels, menus, or areas within your Unity project. Smooth and engaging transitions are vital for creating a seamless player experience, preventing jarring cuts and maintaining immersion throughout the game. Throughout this video, we'll cover project structure, prefabs, modular scripting, scriptable objects, interfaces, and various scene transition techniques. Let's begin with project structure, which is the foundation of any modular Unity project. A well-organized project saves time and reduces confusion. Always create dedicated folders for different asset types. For instance, a scripts folder should contain all your C# scripts. Similarly, establish folders for prefabs, materials, textures, audio, and scenes to keep your assets neatly categorized and easily accessible. Next, we introduce prefabs, which are reusable game objects that serve as templates for creating instances in your scenes. To create a prefab, simply drag a game object from your hierarchy window into the project window, ideally into your prefabs folder. You can then drag multiple instances of this prefab back into your scene, each linked to the original prefab asset. The power of prefabs lies in their ability to propagate changes. Modify the original prefab, and all its instances in your scenes will update automatically. If you make changes to an instance in the scene, these are considered overrides. You can apply these overrides back to the original prefab. Prefab variants allow you to create variations of a base prefab, inheriting its properties while allowing specific modifications for different contexts. Now, let's delve into modular scripting using C# and Visual Studio, a cornerstone of maintainable and scalable game logic. The Single Responsibility Principle, or SRP, dictates that each class or module should have only one reason to change, focusing on a single, well-defined task. For a player character, instead of one monolithic script, create a player movement script solely responsible for handling character locomotion. Similarly, a player health script would manage only health-related logic, such as taking damage, healing, and checking for death conditions. And a player input script would exclusively handle input detection, separating input concerns from the actual actions performed by the player. Modular scripts often need to communicate. Events and delegates in C# provide a powerful, decoupled way for scripts to interact without direct references. To implement a simple event system, define a public static event in a central manager script, which other scripts can then subscribe to. Scripts interested in these events can subscribe to them in their onEnable method and unsubscribe and onDisable to prevent memory leaks. Moving on, scriptable objects are powerful Unity assets that allow you to store large amounts of data independently from game objects. To create a custom scriptable object, define a C# class inheriting from scriptable object and add the Create Asset Menu attribute. You can then create instances of this scriptable object directly in the Unity editor via the Create menu in your project window. Use scriptable objects for game data like item definitions, enemy stats, quest details, or configuration settings, making them easily editable. Components can then reference these scriptable object assets, accessing their data without needing to duplicate it across multiple game objects. The primary benefit of scriptable objects is enabling a data-driven design, where game logic is separated from game data, promoting reusability and flexibility. Interfaces in C# are another powerful tool for modular design, defining a contract that classes must adhere to without specifying implementation details. For example, an iDamageable interface could define a takeDamage method, ensuring any object implementing it can receive damage. A player health or enemy health component can then implement this iDamageable interface, providing its own specific take damage logic. This allows you to write code that interacts with any damageable object, promoting loose coupling and making your systems highly extensible. While similar, abstract classes provide a base implementation that can be inherited and extended, whereas interfaces only define a contract. Dependency injection is an advanced technique where objects receive their dependencies from an external source, further decoupling components and improving testability. Now, let's transition to implementing scene transitions, starting with the fundamental SceneManager.loadScene method for basic scene loading. Create a simple C# script, perhaps named SceneLoader, with a public method that takes a scene name or index and calls SceneManager.loadScene. Attach this script to a game object, then set up a UI button's onClick event to call your load-specific scene method, passing the desired scene name. For larger scenes, asynchronous loading using SceneManager.loadSceneAsync is preferred, as it prevents the game from freezing during the loading process. You can display loading progress to the player by monitoring the progress property of the async operation and updating a UI slider or text element. To create a smooth visual transition, we can implement a fade effect using a full-screen UI image element that changes its opacity. Write a coroutine in Visual Studio that gradually changes the alpha value of this UI image from transparent to opaque for a fade out, and vice versa for a fade in. Attach this fade script to a game object and use Don't Destroy on load to ensure it persists across scenes, managing transitions seamlessly. Integrate the fade coroutines with your scene loading logic. Calling fade out before loading and fade in after the new scene is fully loaded. Beyond simple fades, Unity's animation controllers offer powerful ways to create dynamic and visually rich scene transitions. Design a dedicated loading screen UI panel with elements like a logo, progress bar, and animated decorations. Use the animator window to create animation clips for this panel, such as sliding in, scaling up, or fading in its various components. Trigger these animations from your scene loading script using Animator, Play, or by setting Boolean parameters to control transitions between animation states. For vast open world or large-scale environments, additive scene loading allows you to load multiple scenes simultaneously to form a larger environment. You can load multiple scenes using SceneManager.loadSceneAsync with Load Scene mode, additive, combining them into your current active scene. To remove a loaded scene, use SceneManager.unloadSceneAsync, which is crucial for managing memory and performance in dynamic environments. Managing the active scene is important for lighting and physics. Use SceneManager.setActiveScene to designate which scene is primary. For robust transitions, consider a dedicated Transition Manager script that orchestrates all aspects: fading, loading, and animation sequences. This manager centralizes transition logic, making it easier to modify, debug, and ensure consistency across your entire game. Utilize events within your transition manager to notify other systems when a transition starts, completes, or encounters an error. Beyond basic fades, explore custom transition effects using shaders or post-processing volumes for unique visual styles. When transferring data between scenes, use player prefs for simple data or a persistent singleton pattern for more complex game state. Always ensure your scene management is robust. Handle edge cases like loading a non-existent scene or interrupting a transition gracefully. A crucial tip: always test your scene transitions thoroughly in various scenarios to ensure they are smooth, responsive, and bug-free. Performance optimization is paramount. Avoid loading unnecessary assets during transitions to keep frame rates high and prevent hitches. Utilize Unity's asset bundles or addressable system for efficient, on-demand asset loading, especially in games with a large number of assets. Implement robust error handling for scene loading, such as displaying a fallback message if a scene fails to load, to improve user experience. Finally, always back up your project regularly. Version control systems like Git are invaluable for tracking changes and collaborating effectively. By applying these modular architecture principles and mastering scene transitions, you'll build robust, scalable, and engaging Unity 3D games. Thank you for joining us. We hope this guide empowers you to create incredible and immersive experiences in Unity 3D.